Right. Hello. Hello, everyone. My name is Luis Espírito Santo, and I would like to welcome you to our second online event of 2021. As you may already know, some of you may already know, Deep Learning Sessions Lisbon, or DLSCL, is a group centered in Lisbon which aims at building a network of deep learning enthusiasts for knowledge sharing, creating a space to share and bring visibility to recent developments, and helping people entering and catching up with the news in the broad field of deep learning. I would like to, first of all, thank you all for joining us in this session. And I would like to remind you the format of this event. The presentation will take approximately 1 hour, and it will be followed by a 10 or 15 minute session of questions and answers. You can place your questions in the YouTube chat, and we'll take a look at the end of the session, and we'll answer your questions. Today we're glad to have Professor Francisco Melo, a senior researcher at INESC-ID and associate professor at the Computer Science Department of Instituto Superior Técnico, where he teaches courses on decision-making and AI. Professor Francisco Melo completed his PhD in electrical and computer engineering in 2007 at IST, and since then he has held appointments in the Computer Vision Lab of the Institute for Systems and Robotics in Lisbon, and in the Computer Science Department of Carnegie Mellon University. His research addresses problems within decision-making and machine learning, particularly on reinforcement learning, as well as planning under uncertainty and multi-agent systems. Professor Francisco Melo, by presenting us the foundations of reinforcement learning, is here to guide us into the widely growing field of deep reinforcement learning that have achieved amazing results in robotics and playing games agents. Thank you very much for joining us, Professor. And you may now let me share your presentation. And yeah.
Okay, thank you so much, Luis, for the introduction. And thank you for inviting me to give this presentation. So as Luis said, I'm a professor at IST and a researcher at INESC, and most of my research revolves around, directly or indirectly, the topic of reinforcement learning. So when I was invited to give this presentation, I immediately thought, well, this is a good opportunity to provide an introductory presentation about reinforcement learning. But as I was preparing the presentation, I actually realized that the time span was actually too small to tell everything that there is to know about reinforcement learning, because it's a very wide field. So this will actually be an introduction to an introduction to reinforcement learning. And what I will try to do is to give an overview about some key ideas in reinforcement learning and the intuition behind the main algorithms in reinforcement learning. So this is what the talk will look like. I will first try to convey to you what a reinforcement learning is, what reinforcement learning problem is, and then we will go into ways of solving these reinforcement learning problems using classic ideas, and then using the more recent methods from deep reinforcement learning. We will also be talking about some caveats that we should bear in mind when working with reinforcement learning, and then we will also talk about some fun stuff that we can do with reinforcement learning. So in my presentation, I'm going to assume that you know nothing or next to nothing about reinforcement learning, so I'll really go over the basics. I will try not to get too technical, but at some point I will need to be a little bit technical. But hopefully those of you that know nothing about reinforcement learning will be able to follow, and those of you that already are comfortable with reinforcement learning, hopefully towards the end of the talk, you'll also find something that is of interest. So let's start about thinking about what a reinforcement learning problem looks like. So let's say that this orange cartoon is you, and you are sitting in place number 1. There's a bunch of places from 1 to 9, and you have something to do, but you just don't really know what this something is. For example, you are playing a new game and you don't really know what the goal of the game is. And you know that you have 5 actions available. And for now, let's just call these actions A, B, C, D, and E. So the first thing you decide to do is, well, let's try something and see what happens. So you try action A. There you are, trying action A. And you realize that nothing happens. So you try action B, and when you do, you end up in place number 4. There you are. Then you try action C. You end up in place number 5. You try action D and end up in place number 4. You try action E, nothing happens. You try action A again, go back to place number 1, and you keep doing this, trying things and seeing what happens. And after a while, you start to get a grasp of how things work. So what the different actions do in the different places. And actually, at some point, when you are in place number 8, you try action D. And as a result of that, you end up in place number 7, and you get a prize of €5. So hooray, seems that you've done something nice. For example, if you're a taxi driver, maybe you dropped your passenger finally at its intended goal, and you got paid for that. So what's next? Well, 2 reasonable things that you can do is, perhaps you want to stay in place number 7. Maybe you will get paid more and you will get a lot more money. Another reasonable thing that you can do is try to explore a little bit more and see if there's a hidden treasure somewhere else. And any of these 2 options seems reasonable in a way. And in reinforcement learning, you will often, in designing your algorithms, you will often struggle with this dilemma. Where should we stop trying things, and when should we start taking advantage of what we already know, or should we keep exploring and learning new things? This is what is called the exploration versus exploitation dilemma. I will not get too much into that today. Just keep this in mind, that it's important that we know how to efficiently explore, but we also need to know when to stop exploring. So from this example, there are a couple of takeaways that I would like to highlight. The first takeaway is that everything would have been much easier if we knew beforehand these connections between these places that I'm showing here. It would be even easier if I had actually arranged these places in this particular way, and instead of calling these actions A, B, C, D, and E, I would say that these actions are actually up, down, right, left, and stay. Okay? So everything would have been much easier if we knew what our actions do. Unfortunately, we didn't. And in a reinforcement learning problem, typically this is what happens. We don't really know what the actions do. It would also have been nice if we knew where the money and where the diamonds are, because that way we could try to maybe be more effective in reaching these valuable places. So most of the time, in reinforcement learning problems, we also don't know this. We don't know where the value is. We don't know where the money is. And a third takeaway is that if the world doesn't change, and if the money and the diamonds don't move, if you keep trying and seeing what happens, after some time, you'd eventually figure out everything that you can see in this picture, what the actions do, how to move about this environment, and where the money is. And this is what reinforcement learning is. Reinforcement learning is all about figuring out, by trial and error, how to solve a problem that takes multiple steps to be solved, without really knowing what your actions do and without knowing what the goal is. So in order to describe a reinforcement learning problem, there are some key ingredients. The first ingredient is the state. What exactly are the states? Well, a state describes a situation where you have to select some action, okay? And essentially what the state has is the information that you need in order to do that, to select that action. So in the case of this small grid world that we've looked at before, every time that you need to make a decision, you need to have information. And in this case, because decisions consist of moving about here, what is the relevant information that you need to know? Well, you need to know where you are. So that's what the states would be. The states would be the positions where you can be. If you have a more complicated domain, for example, Tetris, when you need to make a decision, well, basically every tick you need to make to decide what action to do next. And what do you need to know? Well, you need to know the height of the pile, whether there are holes in the pile or not, what's the shape of the pile, where the current piece is, what's the rotation of the piece. So all that information should be in the states. So the states would be all the possible configurations of this screen that you can see here. And if you have a game like this one, so this is the breakout game from Atari, and the goal here is for you to move a red paddle that's here on the bottom in order to hit this wall, which is this small pixel that you see here in the middle of the screen, in order to break this wall, which is sort of a rainbow wall. So what do you need to know in order to be able to decide how to play this game, what action you should do? Well, you need to know where your paddle is, you need to know where the ball is, how the wall looks like, but more than knowing where the ball is, you actually need to know how the ball is moving. So if you just look, for example, at this frame here on the screen, this doesn't give you enough information because you don't know whether the ball is moving up or down, whether the ball is moving left or right. So actually, this single frame does not convey all the information that the state should have. Okay, we'll come back to this particular example more towards the end of the talk. But hopefully by now you sort of get a grasp of what the state should be. Basically, it's a description of the information that you need to make your decision. You also need to know what the actions are. So the actions are basically how you can act in the world. So this is another key ingredient of reinforcement learning problem. In this grid scenario, the actions are just shown here on the left. So now here in red is just going up, down, left, right, or staying. In Tetris, the actions are just the movements that you can make with the piece, rotation, moving left, right, dropping the piece. And in the Atari game, basically the actions are whatever you can do with the control. Another key element of reinforcement learning problem are the dynamics. And by dynamics, what I mean is, how do your actions affect the world? How do your actions change what's around you? And unfortunately, in reinforcement learning, typically we do not know this. This is one of the things that we need to figure out. Another ingredient is the goal. So what are you trying to do? What is the problem that you're trying to solve? And in reinforcement learning, usually we also do not know this, okay? So these are some key ingredients that we have in a reinforcement learning problem. And finally, there's some way of measuring our performance. In a game, it can be the total score. In some other task, it may be whatever money we collect, considering inflation. So these are the 5 key ingredients that we will have in all reinforcement learning problems. And the way we solve these problems is then by having our algorithms, our agents, interact with the environment, try different things, and see what happens. And the way this interaction proceeds is sort of described in this picture here. So our agent will observe the state at each moment. Okay, so the state is this ST here. And based on that state, it will select an action. Okay, so the action is this A of T. And then that action will cause the environment to change, and it will cause the agent to receive some reward, which may be 0 or maybe some other value. And this reward implicitly encodes what the agent wants to do, okay? So this interaction that you can see here depicted in this diagram, this is a very well-known diagram. You'll find this diagram everywhere. Every time you hear about reinforcement learning, someone will show this diagram to you. This interaction can be formalized by a model called the Markov decision process. I will not go too much into a Markov decision process, just want you to know this name and tell you that a Markov decision process has these 4 ingredients that you see here in the screen. The states, the actions, the dynamics, which are this P here, and the goal, which is the reward, okay? And solving a reinforcement learning problem essentially consists of figuring out a way of selecting actions. Okay, so that's what we call a policy. A policy, you can think of a policy just as a box that takes states and outputs actions. Okay, so what the agent does at every moment is it looks at its current state and it selects its next action using some policy. And what we want to do is to figure out a policy that is good in some way. Okay, so if we use the symbols from before, the state is just ST, the action is just AT, and the policy we usually use pi to denote this policy. Okay, and we want to find a policy that is good in some way. And what way is that? That's what we call our performance measure. And basically, the intuition behind the performance measure that we will use is very simple. We want to get as much reward as possible. That's what you see here in this expression. It's just a sum of rewards. And you will see that there's this factor here, gamma, and you can think of this gamma as an inflation, okay? It's called the discount. But what it's saying is that a reward today is worth more than a reward tomorrow. Or to say it differently, the agent wants to have as much reward as possible as soon as possible. Okay, but because there's all sorts of randomness in the environment, the rewards may be random, the way that the environment evolves may be random, we usually put an expectation here just because of uncertainty. Okay, so these are all the ingredients that we need. States, the actions, there are some dynamics that the agent doesn't know, some rewards that somehow encode the goal, and then there's this measure of performance, which is how much reward can the agent get all throughout the time, okay? And we can actually depict this in a more visual way as follows. So let's say that we fix some policy. So the agent is selecting the actions in a predefined way, okay? And at some time step 0, at the beginning of time, it's in some state that I'm going to call S0, so it's this circle that you see here. So following its policy, the agent will then select an action A0. Okay, you see here, it's this circle. And as soon as the agent does this action, what happens is that the state eventually changes, okay? The environment transitions to some new state, which we will call S1, and the agent will get a reward. And now the process repeats. In this new state, the agent will select a new action. This action will cause the state eventually to change. The agent will get another reward. But now, because this reward comes later in time, it will be afflicted by inflation. That's what this little thingy here is representing. Okay, so this reward will be worth slightly less than if it had come at the first time step. And the process just continues, okay? So then another action transitions to another state, another reward. This reward will now be afflicted by inflation 2 times because it's coming 2 time steps later, and so on and so forth. And this continues all the way to infinity, okay? So this trajectory that you see here represented by this diagram, okay, which starts in some state S0 and is obtained just by following some policy pi, this is what we call a rollout, okay? We start in some state S0 and then we just let the agent run. And we can actually use this rollout and look at all these rewards that appear here, duly afflicted by inflation, to get an estimate of how good we are doing, okay? So we just add all of these rewards. Okay, so this is the quantity that we get in the end. And this, in a sense, gives us an idea whether we are doing well or not. Okay, so if we get a big reward, then this means that this policy is actually okay. If we have a low reward, maybe this policy is not so good. And if we want to have a really good estimate of this value, you can actually do this multiple times. Okay, so we start once again in that same state, we do the action prescribed by our policy, which will hopefully be the same. And then we repeat this whole process. And this time, the trajectory will probably be different because of all the randomness involved. So we will get a slightly different value, okay? And if we take into consideration all these values that we can have, sort of average them out, we get how much we expect to get if we follow this policy. And this is what we will denote by Q, okay? So we will use this letter Q to denote how much we expect to get in terms of reward if we follow a particular policy pi, hence this pi that appears here. If we start in some state, S0, and our first action is A0, okay? It's just a little bit of nomenclature, and you may wonder, why should we care about this Q? What does it matter? Well, from what we've seen, what this Q really is just how much we expect to get, okay, in expectation. If we start in a particular state, our first action is just A, and then we follow some fixed policy, okay? So this is what Q means. And the reason for the letter Q is that you can think of it as a quality of this action in the state. But the nice thing about this Q is that it actually provides a long-term evaluation of the actions, okay? It tells us how good a particular action is in a state, taking into consideration the long-term effects of the actions, okay? And we can actually use it to figure out the best actions to take, okay? And just one detail is that it verifies this nice relation. Don't worry too much about that. We will use this later on in these slides, but just keep in mind that this Q verifies this nice relation, okay, which is the expectation of the reward plus Q at the next state and action, if we are in some state and action, okay? So let's see what the Q looks like for this example that we have here. So we have these 9 states, which are these 9 positions. We have these 5 actions. So in this case, we will have one value for every pair of state and action. So we can actually represent this in sort of a table. And let's see what the values are if the policy pi just selects actions randomly. Okay? So this is what Q values look like. And you will see that we have one row for each state, one column for each action. I'm not green, the action with the largest value, okay? So in state 1, the action with the largest value is right. In state 2, the action with the largest value is right, and so on and so forth. And if you look at this carefully, you will see that what these actions in green do is actually take the agent towards the closest rewarding state, so either 7 or 3. And because 3 is worth slightly more, in 1 it will prefer to go to 3 rather than 7. In 5 it will prefer to go to 3 rather than 7. But in 8 it will prefer to go to 7. Okay, and this is because the agent expects that after this first action, the actions will be selected randomly. So the best thing to do is just try to move to the closest rewarding state, okay? And if the agent doesn't select the actions randomly, but it actually selects them in a meaningful way, trying to get as much reward as possible, the values will be much larger, okay? I show them now in this table, and you will see here now that in every state, what the agent tries to do is to move to 3. Okay, as quickly as possible. So this Q, these values that I'm showing here, actually give us a lot of information about how we should select our actions. Okay, so they are very important if we now want to solve these reinforcement learning problems. And you will see that these first methods that I'll tell you about all revolve around this Q function. Okay, so with this, we get into the second part of this presentation, which is how to solve these reinforcement learning problems. We sort of now have an idea of what we want to do. How do we actually do it? How do we solve these reinforcement learning problems? So we will depart from this Q that I just introduced, and we'll try to build what I'll call a proto-reinforcement learning algorithm, okay? And the algorithm will be as follows. We start with some policy. Doesn't matter what this policy is. And for this policy, we compute these Qs that we've just seen. Okay, so these values for all the pairs S and A. And you may wonder, how do we do this? But we'll postpone this to later. And then we will use these cues to improve our policy. How do we do that? Well, we compute a new improved policy using this idea that is here. So in each state, we just select the action with the largest Q value, okay? So in the example that I show, those were the actions corresponding to the green cells, okay? And if we do this, the policy that we get is actually better than the previous one. So we keep doing this and we keep improving our policy, getting a policy that is better and better and better and better until we are done, okay? Okay, so we keep repeating this. We start a policy, compute the Qs, get a better policy, compute the Qs, get a better policy until we get done. So the open question remaining is how exactly do we compute these Qs? Okay. So what we may say, okay, I don't really know how to compute this, but maybe I can borrow some ideas, for example, from, I don't know, supervised learning, okay? So if I have some samples of these Q, I can try to get some function Q hat, which minimizes some square loss. This is what I would do if this was a supervised learning problem. And then I could use, for example, stochastic gradient descent, and I would end up with something that looks like this. Okay, so our updated Q is just the previous one plus some step times this difference between what we would like to have and what we actually have. Okay. Now the problem with this naive idea is that we don't have these Qs, right? We don't have these samples that we would use in our algorithm, because if we had, then basically that's what we wanted to compute in the first place. So how can we solve this? How can we still perhaps use some of this idea, but dealing with the fact that we don't have the Qs to put here? So what we will try to do is we will replace these Qs that we don't have by some good alternatives. So one first alternative, one idea, is to use the rollouts. Remember? And we've seen the rollouts a while ago. So remember, if the Q is just the expectation of this sum of rewards, we've seen that if we start in some state and then just follow this fixed policy for a number of times, what we get in the end is just a sum of policy. So we can look at this as sort of a sample of what we want to compute. So if we take this and put it instead of that Q that we don't know, if we use this as the target for our, let's say, supervised learning algorithm, we end up with an algorithm that looks like this. So our updated Q is just the previous Q plus a step times this return, okay, minus our current estimate. And then we just do this for a number of times until we have some nice estimates for the Q, and then we use this Q to improve our policy, and we repeat, okay? So this idea is actually behind a number of algorithms that all look pretty much like this, and they are called Monte-Carlo reinforcement learning. And Monte-Carlo just because we are using these rollouts to get estimates of the value that we actually want to compute, okay? And this is a very simple algorithm. It works pretty well. However, it has one problem, okay? Because we use these returns as the targets for our updates, we would like these sums to be as large as possible. So we would like this t to be as large as possible so that we have very good, a better estimate. But the problem is that the longer these trajectories are, the larger this t is, the more randomness will be involved. So this value will have a large variance for large t's. So what this means is that this algorithm, although it works okay, it actually suffers from quite a bit of variance. So how can we improve this? A second idea is to, instead of using this expression, which is what we did in Monte-Carlo reinforcement learning, basically we use these samples as target. An alternative idea is to use that other expression that I showed you earlier for Q, which is just this reward plus gamma, the Q values at the next state and action. So what if now we use this quantity here as the target, okay? Samples of this quantity as the target. And you will look at this and see, oh, wait, but I also don't know this red term. So what we do is we bootstrap. What does it mean to bootstrap? Well, we use our current estimate in place of this QPy that appears here. So if we do that, we end up with an algorithm that looks like this. So we start with some policy, we interact using this policy for some time, and as we do that, we update our queues using this update that is shown here. So the new queue is just equal queue plus a step times, and this part here is the target that we've just seen in the previous slide. The reward plus gamma, the queues, and the next state in action. But because we don't have the right queues, what we actually use is our current estimate for that. So this is where the bootstrapping is coming in. So we do this for a number of steps, and then we just use these queues to improve our policy and repeat. And this algorithm is quite well known in the reinforcement learning literature and is called SARSA. And the reason why it's called SARSA is pretty straightforward, is that in order for you to do this update, you need a state, an action, a reward, a next state, and the next action. So state, action, reward, state, action. That's why it's called SARSA. And this quantity that you see here in parentheses, okay, is called a temporal difference. And this is quite an important concept in reinforcement learning, since there's a whole bunch of algorithms built around this idea of temporal difference, okay? And you can see here that in this temporal difference, we are already using information about the future. So this action AT plus 1 is the action selected at time step T plus 1 using policy pi. So in SARSA, what we do is we use these temporal differences to update the queue, and then we use the queue to improve the policy. But what if we do the two things at the same time? What if we merge the policy improvement with the update of the queue? Well, if we do that, we end up with an algorithm that looks like this, okay? So the queue is just the old queue plus a step, the reward plus gamma, the queues at the next state, but now the action that you see here is not the next action selected by the policy, but is the action that maximizes the queue at this state, okay? So this algorithm is very similar to SARSA, okay? It just uses a different action here. And this algorithm is called Q-learning. And there are some interesting aspects about this Q-learning algorithm. The first is that it doesn't depend on this policy pi, okay? So we say that it's an off-policy algorithm, okay? It doesn't depend on the policy. Another thing that no matter what the pi is, as long as it's reasonable, this algorithm will actually get us the best queues possible. So the queues for the best policy. And this is very appealing, right? Because we no longer have to be worried about improving our policy. You can just use any policy, let the agent run in the environment, do these updates, and in the end, we get the optimal policy with no extra effort. So let me show you what happens if we run Q-learning in our example. You see that after 5,000 steps, we end up with values that look like this. Okay? And I know that you didn't memorize the previous ones, but later on, the slides will be available, and you can actually try to look and compare. And you will notice that the values are very close for most of the states. But the most important thing is that if we look at the action with the largest value in each of the states, you'll see that all these actions are actually optimal. Not all actions, not all optimal actions have been identified, okay? So for example, in state 4, you can either go up or go right, but it only identified right at this point, okay? If you let it run for a longer period of time, perhaps it will figure out that up is also good, but at this point, it just figured out that right is good. But the important thing is that if the agent follows these actions, it will actually do as well as it can do, okay? So this is a very appealing algorithm. And these algorithms that I just told you about, Monte-Carlo reinforcement learning, SARSA, Q-learning, these are some of the core classical reinforcement learning algorithms, okay? And they all revolve around computing this Q. So now what happens with all this deep reinforcement learning that we've been hearing about? What are we talking about? Well, let's look at that. In these algorithms that I just told you about, we can represent this Q function using that table, just like we've seen in the example. But most of the time, if we have a very difficult problem with many states, we cannot represent it using a table. So we will need some more sophisticated representation. And this is where deep neural networks can come to help. So let's see how we can put some neural networks into these algorithms. And to do that, let us first revisit the computation of the Qs. In these algorithms that we've seen, the computation always looks something like this. Okay, so we have some targets, and we want our estimate to be as close as possible to the targets. And from here, we derive algorithms that they all look like this, okay, like this update that you see here. And the difference between them is what we choose to be the target. So if we choose the return as the target, then we get Monte-Carlo reinforcement learning. If we choose this R plus gamma Q at the next state of action, we get SARSA. And if we choose R plus gamma Q at the next state in the maximizing action, we get Q learning. So it would stand to reason that if now we have a neural network to represent our Q function, we could use these same ideas to train this neural network. So our algorithm would now look something like this, okay? So the only thing different is this term here, which is just the gradient that we use, we backpropagate and train the network. But other than that, it looks pretty much the same. And if we choose different targets, then we get the algorithms. And to some extent, this is really the case. And I'll show you how this works. But before doing that, let me just make a small note that in the actual implementations, it's more convenient to have a neural network that looks slightly different. So instead of having as input a state and an action and returning the Q value for the state and action, what we usually do is we have a network that has as input the state and outputs the Q values for all the actions, okay? And this is actually more convenient when we want to select the actions, because then we have all the values and we just have to pick the action with the largest value, okay? And we need to do only a single run through the neural network rather than having to run through the neural network once for each action and then selecting the maximum. So this is a more convenient representation, and it's actually what is used. So let's look at what happens with this update here as we choose the different targets. So the first is to use the Monte-Carlo target, which is just return, if you remember. So if we do that, we get an algorithm that looks like this. So we start with some policy, we run some rollouts, and then we just use this gradient descent to train the parameters of the network, and then improve our policy using these new Q values, and we repeat this process. So we get something that looks pretty much like what we had before. It's just that now we are using a neural network to represent our Q function. The same thing happens if we use the SARSA target. So now we get something that looks like this. We just backpropagate these values through the network, and we get a version of SARSA that uses neural networks. We start with some policy, we interact with the environment using this policy for a number of steps, and then we just perform these updates. And once our network has pretty much learned these values, we improve the policy a little bit, and we repeat this process. And the same thing for Q learning. So we take our Q learning target, we just stuck it here, we train this using some policy, and we have a version of Q learning using a neural network. Alas, for Q learning, this doesn't work so well. Okay, so Q-learning is known to diverge in some problems when we use them with function approximation. Okay, so a neural network is a function approximator. So if we try to use Q-learning in this naive way, just in a careless way, our algorithm may not learn anything useful. It may actually just learn garbage. And the reason why this happens is because Q-learning actually falls prey to what is known as the deadly triad. So in Q-learning, we have these three elements conspiring to make the algorithm fail. And these three elements are bootstrapping. Okay, so we have bootstrapping here, remember? When we replace that Q pi by our estimate, we were doing bootstrapping. So in Q-learning, we have bootstrapping. We have off-policy learning, remember? Q-learning is an off-policy algorithm. It doesn't really worry about what policy we use to get these samples. And with a neural network, we get function approximation. And the reason why we haven't gotten any problems so far is that in the previous algorithms that we've seen, at least one of these were missing. So in Monte-Carlo, we don't have bootstrapping. In SARSA, we don't have off-policy learning. And in the previous version of Q-learning, when we were using a tabular representation, we did not have function approximation. So now, when we use the neural network with Q-learning, we get all three, and this may lead to divergence. So what can we do to overcome this problem? Is Q-learning doomed? Well, we can try to get rid of one of these. Function approximation is not something that we can get rid of, right? We need our neural networks to deal with these large problems. Off-policy learning is also quite convenient. It's convenient that we don't have to worry about whatever policy we use to get our samples. So the natural candidate is perhaps bootstrapping. Is that a way that we can get rid of this bootstrapping? And actually, people realize that we can get rid of bootstrapping if we use a second network to compute the targets. Why is that? Because now the targets that we use to train our network no longer use the output of the network. Okay, the second network is called, let's call it the target network. It's just a copy of the main network that is not updated, or at least it's not updated very often. And the resulting algorithm looks something like this. So the update is basically the same as the one we had in Q-learning before we introduced the target network, with the difference that this element here is now computed using the target network. Okay, and this algorithm is what is known as DQN. So DQN was perhaps the first deep reinforcement learning algorithm that was brought to the community's attention with its great success in the Atari games, and we will visit that success in a moment, and was perhaps the father or the mother of all deep reinforcement learning that has been done since then, because it really fostered the excitement of the community about these algorithms. But there's actually something we can object regarding what we've been doing so far, okay? So if we look back at our proto-reinforcement learning problem, it all revolved around this very simple idea. So we started with some policy, we computed or approximated the corresponding Q values, we then improved the policy and repeated. So it was all basically around this. And there are two objections that we can make. First objection is concerned with this way of improving policies. What happens if we have, for example, a continuous number of actions? If we do that, doing this maximization may actually be very difficult. So this improvement step, which we sort of haven't paid much attention to so far, will be all but trivial, okay? And the second objection we may pose is, why should we care about this Q? If we want to compute a good policy, why don't we optimize the policy directly? So these two objections actually lead us to a slightly different family of reinforcement learning algorithms that are built around the policy. So these algorithms that we've seen, they are sort of built around this Q function, And the ones that we're going to see now, they are built around the policy. So if we have a policy that we can adjust with some parameters that we can adjust, then we don't need to worry about this problem of maximizing the actions. And maybe we can get rid of these queues and optimize the policy directly. So how would that work? Let's say that we have a policy that is represented, why not, using a neural network. So in this case, we would have an input, which is a state, okay? The policy is represented as a neural network with some parameters, and the output of the network is just the probability of selecting each of the actions in this particular state. And you will note that the overall structure of this network is not so different from the one we had with the previous algorithms. It's just that now the outputs, instead of being Q values, they are probabilities of selecting these actions. So now what we want to do is to optimize the parameters of this network so that the way that this network selects actions yields very large sum of rewards. Okay, so let's do that. We want to use some gradient descent or gradient ascent to tweak these parameters. And then we are faced with this challenge. So how do we compute this gradient? How do we even compute the gradient of something that looks like this? Well, it turns out that if we massage this expression a little bit, this gradient can actually be computed. And it looks something like this. So I just called it gradient here. And it's just the expectation with respect to our current policy of this big expression shown here. Don't worry too much about this expression. Just note that all the things that appear here are things that are familiar to us. So we have the Q values for the policy, which is something that's familiar to us. We have the policy itself, which is basically our neural network, and we're just computing here the logarithm of this policy and some gradient of the policy, which seems to be also something that is reasonable. Okay, so although this expression looks rather ugly, all the quantities that appear in it are familiar. And the nice thing is that we can actually compute or approximate this quantity, this gradient, using rollouts. And this is the idea behind an algorithm that is called reinforce. Okay. So how does reinforce work? Well, we start with some policy pi theta, okay, so our neural network with some weights. We run some rollouts using this policy, okay, for different states, different initial states, different initial actions. And then we improve our policy using this gradient update, okay. So we just compute here this quantity, which is basically a rollout, where we have the gradient of the logarithm of the policy and this Q estimate. And you may wonder, but what's this Q estimate? Well, we just replace it by another rollout. So we just let the agent run these rollouts and then use the information that it collects to update the parameters of the network. And we repeat this. We do this a number of times. Okay. So this is the reinforce algorithm. And actually, the reinforce algorithm is rather old. It exists since the 80s. But nowadays, and it was used with all sorts of policy representations. But nowadays, it has gained new interest because we now want to represent policies using neural networks, and this algorithm is quite amenable to that representation. And there are all sorts of variations of these algorithms. For example, we can use a different way to estimate Q. Instead of using a rollout, for example, we could use a SARSA update. Okay? And if we did that, we would get an algorithm that looks something like this. We start with some policy, let the agent run with this policy for some time, and then perform these updates. And these updates that you see here, they are just the SARSA updates that we've seen before. Don't worry about all these funny expressions. It's just the SARSA update that we've seen before. And then we use these queues to perform policy updates. And we repeat. Okay. And if you look at this algorithm, you'll actually see that there are here two things being updated. the Q values, which use a SARSA update, and the policy, which use a policy update. So it's like as if this algorithm has two parts, and it's usually referred to as an actor critic algorithm because of these two parts. So we have the actor, which is the part concerning the policy, where we do the policy gradient updates and so on, and we have the critic, which is the part concerning the Q function. Okay. So it can sort of be represented using this diagram that you see here. And with this, we've covered some of the main families of reinforcement learning in their classical version and in their deep version, okay? And recently, with all the advances in deep learning, there are many variations of these algorithms. For example, regarding DQN, even with the target network, there are some issues, there are still some problems of convergence. So there have been a number of variations that have been proposed. For example, choosing the action that maximizes the Q value in the main network, but using the value from the target network. This is what is called double DQN or DDQN. You can actually use a split layer before the output layer in the network, something that looks like this. And there's actually some formal interpretation of what this means. There's some semantics to this, which I will not go into. This is what is called a dueling network. In the actor critic version, in the actor critic algorithm, there are some versions that try to take advantage of distributed computation. So they actually implement a number of sub-algorithms that each interact with the environment independently in a distributed manner, and then there's a global network that tries to combine the contributions from all these sub-algorithms. And also there are versions of policy gradient. We can think of them as versions of policy gradient that try to be more data efficient and reuse data that the agent experienced while using previous versions of the policy that is currently updating. And this is the case for two very well-known algorithms, TRPO and PPO. And so as you can see, there's a lot of work, and it's currently a very exciting field with new papers coming out every day and very amazing successes. But there are also some things that we should be aware if we are working with reinforcement learning. But actually, let's do it like this. Let's start with the fun stuff before we go into the warnings. So let me first show you. I'll try to show you some videos and some funny success stories that we have with reinforcement learning. So, for example, there have been several versions of actor critic and policy gradient algorithms used to control underactuated bodies, which could be robots, but they're typically done in simulation. The input for these networks are usually giant angles, velocities that describe the state of the robot. And the output is control signals for the robot. And this has been used to do control, for example, this humanoid that you see here. So the goal here was for the humanoid to learn how to get up and then follow the target, which is this pink ball. And if it somehow falls down because the target suddenly changed, it learns how to get up. And this was done using PPO. Okay. Let me show you another example. So the famous DQN algorithm that plays the Atari games. So DQN just follows the architecture that we've seen before. The state, as we discussed in the beginning, is not just a frame of the game, because as we've seen, this is not enough to give the agent the information it needs to take the decision. So the way that they did it was, instead of giving it one frame, they give it multiple frames. And by having multiple frames, we can already estimate what the velocity of the ball is. So by using this trick and providing to the network only the pixels, that's the only thing that the network sees, is the pixels. It learned how to play these Atari games. So the outputs are just the controllers, and the neural network is a big network with a number of convolutional layers and some fully connected layers. And it learned to play rather well, as you will see here. So after 100 episodes, it doesn't play really that well. It misses most of the time. Then after 200 episodes, it starts to catch the ball more successfully, as you can see here. Sometimes it misses, but most of the time is able to actually get the ball. After 400 steps, it's actually able to catch the ball all the time, although with some hesitations, but it's actually able to play rather well. But then, after 600 episodes, it figures out that the best way to play the game is actually to dig a tunnel through the wall and let the ball move to the upper part of the screen. There you go. And now the ball just plays the game and you don't really need to do a lot. And the nice thing about DQN, the reason why it was such an extraordinary success was that so far there had been a lot of reinforcement learning algorithms to play these games, but these algorithms required hand-tuned features. Okay, so they relate people to tweak and figure out what are the important features that the algorithm should rely on. And the nice thing about DQN is that it just played using the pixels and it figured out by itself what the important information is. So there were no hand-tuned features. The same architecture was used, and it was able to learn all these games. And it was able to attain superhuman performance for many of the games, so the ones on the left of this vertical line. And it was actually better than algorithms that used fine-tuned features, which correspond to the bars in gray. Okay? And then now, with all the work that has been done on deep learning, there are all sorts of fun things that you can do when you combine these ideas from reinforcement learning with other work that has been done in deep learning. For example, in this work, we did a version of Space Invaders where there's these yellow enemies. There are no protections, and as you can see, it's quite frantic because they're keep firing all the time. And in this game, the enemies emit sounds and the bullets emit sound. And there's the player is actually able to hear it by some microphones that are in the pedal and in the environment. And what we did in this game was to learn a joint model of sound and image. And then, using this model, we trained the algorithm to play using only images. So the reinforcement learning algorithm using only images. And then we tested it giving the algorithm images to play, and this is what happened. As you can see, the sound is quite terrible, but the agent is able to play quite well. And what we did next was to blindfold the agent. So now the only thing that the agent is hearing is the sound, and it never trained with sound. It has never played or learned how to play with sound. And this is what happened. So I don't know if you realize, because the sound is very appalling, but the agent was actually able to play using only sound without ever having trained with sound. Okay, and this is due to the joint model that it learned with image and sound. So to wrap up this talk, there are some important things that you should keep in mind. Is that in spite of all these successes, it's still quite challenging to get these complex reinforcement learning algorithms to work. And there are a number of reasons why this is. First, they require a lot of computation and a lot of time. Okay, and during this time, what the algorithm is doing is just trying stuff. Okay, so as you can see, the scale here in this plot, which compares a number of variations of DQN, is in the millions of the frames. Okay, so as you can imagine, this is a very computationally heavy algorithms, and in a sense, this is not too different from other deep learning algorithms. However, even with the use of neural networks, these algorithms are very sensitive to the way we model the problem, to what we tell the algorithm to be the states, and particularly what we tell the algorithm to be the rewards. And in this video, you can see a bot that was trained using reinforcement learning, supposedly to win this race. It so happens that when the programmers developed this algorithm, they gave the algorithm some small reward for grabbing these boosts, which are these green things that appear in the water, these turbo boosts. So what the algorithm decided was that it was more rewarding to actually circle around and just collect these boosts than to actually bother finishing the race. So designing the reward is actually quite challenging, and it may lead to very strange results. Another aspect that can happen is that because the agents require some trial and error, sometimes they try strange stuff and may get stuck in local minima, and you get things like this. So the goal in this example was for this pseudo robot to learn how to walk as quickly as possible, but it actually figured out how to walk on its back, okay, which is kind of strange and not exactly what the developers were expecting. And another important aspect is that of stability of training and reproducibility. Because in this example, for example, this is from a paper, you can see here that the orange line, this is in the y-axis, this is a reward. The orange line shows that this VMA method is much better than the others. But this shaded region, this corresponds to the variance in the training seeds. So what this means is that with one particular training seed, you may get a performance that looks like this, like the top of this shaded envelope. But with a different seed, you train the exact same algorithm and you get a performance that is like the lower envelope of this training seed. So all this variance, just by changing the seed that you use in training, this is something that is very challenging to deal with, because sometimes it's very difficult to actually assess how well our algorithm is performing. And to conclude, so I hope I was able to give you some ideas and some intuition of what reinforcement learning is all about. Essentially, algorithms to solve sequential problems by trial and error. These problems are usually hard to solve, and deep reinforcement learning offers a great promise because it alleviates us from having to have this, in many situations, it alleviates from having to design features, to hand design features. And we've seen tremendous successes of deep reinforcement learning, but there's still a lot to be learned, a lot to be done. So it's a very dynamic and exciting field to be working in right now. Thank you so much, and I will take your questions now.
Thank you so much for this great and very elucidative presentation. So we already have some questions. I think I can start with this one that is related to this last slide. That's what are the hottest topics or the most important problems in reinforcement learning right now that researchers are trying to approach?
So this is a very good question, and I'm guessing that there are many hot topics, some of which I may not know about, but some of the topics, some of the research that is being done right now, I would venture at least two important topics that are being covered right now. One is not specific to reinforcement learning. It's actually something that worries the community that is doing deep learning, and is the ability to understand what these algorithms are doing. Okay, sometimes when we get a policy coming out of a reinforcement learning algorithm, it's very hard to understand why the algorithm is recommending that we do something. And this is not, as I said, this is not just specific to reinforcement learning. It's something that actually plagues all the deep learning algorithms, is to try to understand and try to interpret and explain what the results are that these algorithms produce. Another challenge, another hot topic in reinforcement learning right now has got to do directly with one of the caveats that I mentioned, the sample efficiency. Because as we go into more and more and more complicated problems, and we need more sophisticated algorithms, we will need more and more and more data. And the idea that I conveyed, where we collect some data, we compute something, then we improve our policy, and we collect some more data, sometimes that's not possible. Sometimes we collect data, and that's it. We don't have the chance to collect any more data. So we have to do with that data whatever we can. And that's actually quite challenging, because we need to, on one hand, to make sure that the data is as complete as possible, so that when we train our policies on that, we get reasonable results. But it raises a lot of questions, even for the learning algorithms themselves, which is, how can we take the best advantage of this data? And how can we have algorithms that try to optimize a policy when the data that it has to optimize it was using some other, maybe completely different policy? Okay, and that's a very challenging problem. It's, some people call it offline reinforcement learning. There have been previous versions of this problem, which was called under the name of batch reinforcement learning. But I would venture that those are at least two hot topics right now. I don't know if they are the hottest.
Yeah, I think everyone got the grasp of all of these two problems that are important nowadays for this field. Let me check here. So we have these questions from Ines that is, how does it shows the action with highest probability policy, or do we compute the set of actions with highest expected reward? I don't know if you...
So this is a good question, and I think that there are two flavors of algorithms, and one for each of these two alternatives. And I try to, if I'm understanding correctly this question, today I try to sort of convey a little bit of the intuition behind these two, so we can think that perhaps policy gradient methods and autocritic methods are perhaps closer to this second alternative, where to this first alternative, where we somehow tweak policy so that it gets as much reward as possible, but then we just select the actions according to the probabilities outputted by the network. But the other class of methods, more based on computing those Q values, they are perhaps closer to the second alternative, where we just try to compute these Q values, and then we just select the actions with the highest expected Q value. So I think that there are these two flavors of methods. There are actually some that probably fall in between, but I think that there are at least methods distinctively do one thing and distinctively do the other. Okay.
All right. So I have here another question about the way we optimize these policies and these functions, and is regarding genetic algorithms. And the question is there any significant use of genetic algorithms in reinforcement learning?
Okay. So I don't know a lot about the use of genetic algorithms in reinforcement learning, so I'll tell what I know, okay? But there may be more. So I know that there have been some years ago, there were people who were doing these algorithms that optimize the policy directly, and this optimization was done using genetic algorithms or other sorts of evolutionary algorithms, maybe not exactly genetic algorithms, but evolutionary algorithms. And there is a branch, at least more in the robotics community, that actually uses these evolutionary algorithms to optimize policies for robots. And in this case, the sort of policies they're trying to optimize are policies used to control, for example, robot arms. And there's not so much this long-term this question of the long-term performance that we typically have in reinforcement learning, like having all these time steps. And in these kinds of scenarios, these black box optimizers like genetic algorithms and evolutionary algorithms, they are very used and with a lot of success. Okay, so algorithms used to optimize policies directly that are used in robots. In the more, let's call it standard reinforcement learning, I know that there have been people that use genetic algorithms to design the neural networks that are then used in the context of these algorithms. Mm-hmm. And I think that there have also been some work that, I was trying to remember, that has got to do also with this aspect of sample efficiency. But right now I can't remember exactly mm-hmm. what they were doing, so I prefer not to say. Okay.
All right. Getting along. So in this topic of resources, someone is asking, what if we have a limited budget to train these reinforcement learning models? Is there any way we can train them? It makes sense to use reinforcement learning models or deep reinforcement learning models when we have limited budget and limited resources?
I would say that depends significantly on the problem. There are particular problems where if you have very good models, because you have them from physics or from other fields of study, that even if they're not perfect, you may make a better use of your data to try to tweak these models and make these models more reliable, and then use other tools to work on the models. Okay, because in reinforcement learning, you're trying to do many things at once. You're trying to optimize your control or your policy. You're trying to learn the dynamics of the world implicitly or explicitly. You're trying to learn what you are trying to optimize, all of this at the same time. So if you have a limited computational budget, or if you have, for example, not so much data, it may be more effective to actually use this to train good models that rely on, I don't know, expert knowledge, and then use tools, not necessarily reinforcement learning. So in the references that I have here, let me move to that slide. So you'll find here a bunch of references regarding some of the algorithms that I've told you about. But there's also here a reference to a post by Alex Ipan, is the second one. And he talks a little bit about all these caveats of reinforcement learning. And one of the things that he discusses is that in some specific problems, there's enough expert knowledge for other tools other than reinforcement learning to be more effective. Unfortunately, there are some problems where you don't have those tools, where you don't have those models. And in that case, you have to do what you can do with the resources that you have. And in this case, the algorithms that I talked today, they're all, we can call them model free. They don't learn a model of the problem that we're trying to solve. But there's actually some work that has been done, some very exciting work, where they try to actually use the data that the agent collects to learn models. The reason why this is a good idea is because if we have these models, then we can do more things with the models than if we just have the data. Okay, they're more, in a sense, they're a little bit more sample efficient to work with than just working directly with the data like we do in DQM and these policy gradient methods. So there has been some work also on model-based methods that to some extent may be slightly more sample efficient. But I would say that it's very problem specific.
Yeah, I think so as well. And on the other side, so if we don't have enough resources, maybe using reinforcement learning is not a good approach. And are there, this is a question of mine. That is, are there any domains, other domains that should take advantage, and probably they have the resources, but are not taking advantage of deep reinforcement learning that you believe it would be good, something like medical imaging or something like this? Do you think you can apply, you can think of a task that would would take advantage of the deep reinforcement learning that is not taking advantage right now?
So that's a very good question, and I don't know if I have a very good answer for you. I think that the other way around is definitely true, and there's actually some work that has been done for a number of years now, where the idea is to try to exploit ideas, for example, from supervised learning to make and bring them to reinforcement learning, because reinforcement learning is actually a very difficult problem. It's difficult in all its facets, let's say. And if we can somehow build on what has been developed in other areas like supervised learning and take advantage of that in reinforcement learning, that can actually lead to interesting results. And there have been results and work on that. Now, areas where reinforcement learning is not being used, well, we can, I think, the way I think about it is that reinforcement learning is just trying to solve optimal control problems. And there's literature and work being done on optimal control from the beginning of the last century, at least. So there's probably a lot of areas where the two fields probably intersect. But at least that I know of, and I may be talking a little bit out of place, there hasn't been so much of a exchange of knowledge between these two, and that would actually be something quite interesting and quite fruitful, I would say.
Okay. Yeah, I think we're reaching the end, so I think I can choose one last question. I think I'll pick this one that is about time. So how much time, how long do you think it will take until these techniques are applied to other domains other than robotics or game playing agents?
Okay, so this is also a very good question. So robots are a natural platform for using reinforcement learning because, as I said, reinforcement learning actually is solving optimal control problems. And games are also good domains because we can do trial and error as we want. But there are definitely other domains where reinforcement learning can be used and has been used. For example, there's a lot of work using reinforcement learning for example, traffic signal control. Okay, because that's also a control problem, and it's very hard to get good models. There are some models for traffic signal control, but they are quite restrictive, and so reinforcement learning has potential there. Of course, that we have the problem of scalability, and there are other problems that come with it, but there has been quite some work and some success stories using reinforcement learning on traffic signal control. And there's also been work on reinforcement learning on dispatching, so inventory management, and other applications. I'd say that as long as you have a problem of control, you can use reinforcement learning. I don't know if I was able to successfully answer that.
I think so. I think we need to close our session. Let me just change this view. So thank you very much, everyone, for being here, for being here with us and joining us in this great session. I would like to inform that the video will be available on YouTube, as well as the slides on our GitHub account. If you may, we would like to ask you to fill the feedback form that is on this the description of this video. because we want to improve our sessions, and this content is for you. So we would like to have your feedback. We also would like to tell you, if you have a presentation or some project that you want, or know someone that have some projects that would like to show and present in such a session, you can reach out to us in this other form that is also linked down below, or you can just reach out through our email. And once again, thank you, Professor Francisco. And well, I hope everyone enjoyed this session, and you got a better grasp on deep reinforcement learning, or at least the foundations of reinforcement learning and deep reinforcement learning. And I hope to see you all in our next events that we are preparing for you. Thank you very much, and stay tuned.
And thank you once again for the invitation. Bye-bye.
Bye.